to learn today, but we'll present it in a nice way, and everyone will understand everything. It's really important to us that you will ask questions if you don't catch up, and we'll help you understand. Okay, let's begin.
Let's have fun, guys. Let's start.
I'm not sure about the fun, but okay.
We'll try to have fun.
Okay.
Okay, so first we'll present the motivation behind using node pair sampling over other clustering methods. So the main points are that the fact that this is a localized analysis of relationships. By that I mean that since we are using node pair sampling, which means pair is a zoom. So since we are using pairs, we are able to see smaller resolution patterns in the graph. And therefore we can see both high resolution and low resolution, which is the second point, actually. The fact that there is a problem called avoidance of resolution limit. The resolution limit is the fact that in large graph, you might lose small patterns, which mean that if you have a small cluster within a big graph, you may actually lose this information, and you will merge the small cluster into a bigger cluster, and therefore lose information in the data. So by using node pair sampling, you will be able to keep this information and not merge eventually those clusters. And it's improved accuracy in community detection. This is after researches and actual tries. We see that we have a better results for community detection. In our presentation, community will sometimes used instead of clusters because in this type of
Johan, please explain what means community detection. I'm not sure that everyone is familiar with this term.
Yeah. So community detection actually mean in a graph. So it's for us, community is like a cluster. It's like if you have a graph with a lot of let's say peoples and social media, etc., or maybe some people follow other peoples, then a community might be all the science guys. So if you follow a lot of science people, you can see a community of science on a high resolution, or you can go deeper in the community and you can see that all those people follow only this guy or this person. So community in our presentation sometimes mean a cluster for us in the seminar.
Okay, so we'll give you examples of where it's actually come in handy. We can use it in gene-protein interactions because when you inspect genes, the proteins interact in pairs. So it's really important to give pairs a higher value instead of like, let's take in comparison k-means that we've learned in this seminar. We take a whole group and we consider every node in the group. Over here, we just inspect only small node with another, and that's how the genes, the proteins work as well as in co-authorship networks. Let's consider, I don't know, or made a paper with Ran Dubin and with Wojciechowicz. And so that way, because they interact with each other, we can see clusters of, I don't know, researchers from Ariel, researchers from Beersheba, and so on and so on. And user item relationship, like in, I don't know, Facebook or Instagram, something like that. When we can see communities and so on.
So our presentation will follow those steps. We will first showcase the Louvain algorithm, which is our comparison algorithm in the field of hierarchical clustering. Louvain is and clustering in general. Louvain is used widely to compare results. So we will first explain what is Louvain, and therefore in the next steps of the presentation, we will see how our algorithm compared to Louvain and why our algorithm helps to overcome some issues that you have with Louvain. Then we will introduce you to hierarchical clustering in general, so everyone understand well how it works. Then we will see our own paper, which is hierarchical graph clustering by node pair sampling. We will present the algorithm, the idea behind it, and we will then showcase a code with some results. We'll have some time for questions and to understand everything. And finally, we will compare our algorithm results and the Louvain algorithm results on the actual data.
Yeah. Okay, let's start with Louvain. It's a bit mathematics, so let's go slow, and everyone feel free to ask questions. Okay, so the method to detect communities, we said it before, it's clusters. It's by maximizing modularity. Modularity, as you can see, it's the term over here. We'll explain it in the next slide. But what we're going to do is we're going to initialize clusters. Each node will be clusters. And as long as the modularity keeps getting better, we'll make another iteration. We will just stop when we are not getting better with the clusters and the modularity is getting better. So how it's going to be? When we meet a node, let's say we are in the first node, first cluster, and the second cluster, and we merge them. We're gonna do something called aggregation. Aggregation is a term for merging, and also it calculates the combined value of the cluster. Let's say I don't know, first node and second node, each of them had a weight of 2, so the merged weight will be 4, for example. It's actually more complex. We'll say more about it in our presentation, but for now, that's how it goes. And after we'll finish all of that and the modularity stopped rising, we'll return the algorithm. And note, Louvain algorithm is not a hierarchical graph, hierarchical algorithm. It doesn't put a dendrogram. We'll learn what's dendrogram and everything in the next couple of slides after Louvain. But just keep in mind, Louvain algorithm is not a hierarchical algorithm.
Okay. So I just want to add that here modularity is signed by the letter Q.
Johan, you have a
Yes.
question. You have a question.
Someone asked me?
Yeah, I wanted to ask if you can visualize the formula a little bit. If you are doing it later, it's okay, but I just want to know how the whole process works of the clustering.
Modularity will be explained in the next slide.
In the next slide, we will understand the formula and how it works.
Okay.
So I just wanted to say that the letter Q here is to say this is our quality metric. So for us, as greater the Q, the quality, the better it is. So we want actually to maximize this parameter. So this is the notations. I will explain it by myself, but you have everything right over there. So firstly, we have this term to say that we are doing an average over 2m because we are counting twice every edge. So we actually divide by 2m. Then we are summing over a term times an indicator. The indicator, I will explain it briefly, but I will focus mainly on this term. So we are summing above all the edges. So Aij is the edge ij between two nodes, I and j, as right here. This is the ij cell in an adjacency matrix. So Aij is the weight of the edge in the actual graph, minus gamma, I keep it for later, and this term is the expectation of an edge in a random graph, which means we are comparing the expectation value of the weight in the graph compared to what our graph is actually. So what we are doing is what the purpose of the quality is compare ourselves and compare the probability random graph. And while we are doing better than random, we don't need to stop because we know that we are doing better than random. And the indicator is here to say if we decided that I and J, which is this edge, are in the same cluster after we run Louvain, we count this term. Otherwise, this is zero, and therefore this will add 0 to the quality. So I will do a recap. We are doing an average of what our cluster actually give compared to the random graph. I know this is the complicated part, but if you have a question, please ask me. I want to make it as clear as possible. Everyone understood the quality metric and the idea behind it?
We'll explain about the gamma over here.
Yeah, the
next
gamma.
slide. But the overall idea is to check if we're better than a random. That's the overall idea.
Okay.
You got it, Yarin?
Yeah.
Okay.
Thanks.
Can you open Okay. So let's explain the gamma parameter. First of all, we can see here two groups, let's say two graphs, and we can see over here we got bigger clusters for overall, and over here we got smaller clusters. Those are in the same color, and those are in the same color, but it's different colors. It's different clusters. That's a presentation of the difference in gamma. When we have a small gamma, we'll have larger clusters.
So
Because
Matan,
what?
in your eyes, the gamma parameter is an equivalent to the radius of a circle?
The gamma parameter is it's the resolution parameter.
Hey, like the radius of a circle.
Yeah, we can.
Okay.
So as small as the gamma, as the largest the cluster will be. If we'll take, for example, a very large, a very small gamma, we'll have just one cluster, for example. We can see over here a graph that shows how many clusters. This is the cluster axis, and this is the resolution axis. And as the gamma rises, we got more and more clusters. And as the gamma is smaller, we got a few. That's how it goes.
I want to add some info about it. If you see, the gamma parameter is a factor of the random expectation. Therefore, if we are giving a high value to the probabilistic to the expectation, then our algorithm will stop sooner, because sooner we consider that the probability expectation is better. And if if we are using a small gamma, sorry, no, opposite, sorry. If you use a small gamma, then you will stop later in the algorithm. Therefore, you have bigger clusters because you give low weight to the probability part. And if you have large gamma, then you are giving a huge weight to the expectation, and therefore, really early, you will actually have the maximum quality because you are subtracting the big value, and you will try to subtract to the quality. And this is help us to see big patterns. Like if you have a city-like database, you have let's say you have the database that have a city. So if you use a small gamma, you will have like one city in one cluster, one city in another cluster, one city in another cluster. And if you use a larger gamma, you will have like this is one city, and this is one neighborhood, one neighborhood, one neighborhood. And therefore, using your gamma, you can choose what kind of cluster do you want? Do you want bigger cluster or smaller cluster? Do you want to add something?
No.
No.
Very good.
Let's go to the next.
Can I have a question?
Yes,
Yes,
of course.
כאילו הגודל הגמא משפיעה כאילו על גודל הקלאסטרים, ואז זה משפיע גם על כמות הקלאסטרים, כאילו זה מוביל לזה שיש כמות יותר גדולה של קלאסטרים.
Because we have a same amount of nodes, when we have larger clusters, we can split the amount of nodes to just a fewer clusters overall.
Yeah.
So as you can see over here, it's the same graph, but because the gamma is small, we got larger clusters. So that's in a result, it makes it we have a small fewer clusters.
Mm-hmm. It makes the algorithm stop later. So after we merge the lot, we have few clusters.
Yeah.
But if we stop early, we still have a lot of clusters. So it impacts when we stop to iterate.
Yeah, do you remember the before we got yeah, over here we said we're stopping iterating when the modularity stops rising. So if we stop the modularity stop rising earlier, we want to make more iteration and therefore more clusters, less clusters. Okay.
Thank you.
I also wanted to ask another thing, if you have time for it.
Mm-hmm.
You said if we have a smaller gamma, we proceed with the algorithm and we make more iterations and
Yes.
more aggregate,
Yeah.
right?
Mm-hmm.
I
Yeah,
wanted
right.
to ask what actually stops the algorithm. What is the condition you stop?
Oh, you just explained it right
Yeah.
now. When the quality, which is this formula, when this quality metrics stop to rise, which means we are not improving anymore the quality, this formula according to the probabilistic part. So if we change the gamma, we change the weight of the probabilistic weight. So if we give this a huge value, we will stop earlier because this part will have, which is in minus, right? So this part will start to make our quality go down instead of go up. This therefore we will stop earlier.
So if I understand you correctly,
Mm-hmm.
the last iteration, which gives you a value of less than the last iteration, so
Yes.
you go back one step, if I understand you correctly,
Yes.
Yes, exactly.
and
We
then
don't
you
stop.
stop.
Yeah, we stop when the modularity stops rising, and therefore, if we got a worse modularity, we don't count that step.
Okay, so you go to the n-1 step.
No, it doesn't necessarily have to be minus one, because if we have a node, yeah, we can stop I don't know halfway, or we don't go all the way to
Mm-hmm.
merge it to one node. We just stop when the modularity stops rising.
Okay, thank you.
I have a question. מה המשמעות של ה-quality, כאילו, על מה זה בעצם מעיד הנוסחה הזאת? ועוד שאלה, למה אתם משתמשים בגרף הרנדומי?
This is actually the same questions because you actually those are related. This is a nice question. So this part is I will come back to this part. Okay, we have the degrees of the node I and J. Okay, so this is the degree times the degree of the other nodes divided by twice the number of edges, which is actually the expectation. You know, it's a tochelet. It's the expectation of the random graph for this cluster, the number of edges in a random graph between I and J. So what we are actually comparing is how a random graph is doing compared to our graph, which is Aij, which is the current graph. When our graph have a lot of edges in between two nodes, it means that there is a cluster here, right? because if there is no edges between two nodes, this means that they are not related. So if actually our matrix have a lot of edges between a pair of nodes, that means that there is something interesting that is not randomly created and there is a pattern over there. Do you understand? Sorry, I did not hear it.
אמרתי כן.
Okay, so
nice.
we'll keep going. So, okay.
Okay, so now one of our main questions is how do you know, and is it possible to know before running Louvain algorithm, what gamma do you want? Because you have a graph that you don't know anything about it, right? So do you think of a way maybe of knowing which gamma you want there, or do you need to try? What do you guys think?
בגלל שגמא בעצם קובעת לנו איזה גודל קלאסטרים יותר גדולים או יותר קטנים, כשאתה בא סתם לדוגמה, אם אתה רוצה קלאסטרים שהם יותר קטנים, אז אתה כן תדע מראש את הערך של גמא.
But do you know a precise value of gamma?
לא, אני לא יודעת.
And also you don't know, maybe your graph have small patterns that you want to keep, maybe there is bigger pattern that you want to keep. Yeah, if you know beforehand that your data consists of, I will say 100 clusters compared to number of nodes, of course. But if you have a 100 cluster, maybe you will know beforehand that you want a range of smaller clusters.
Yeah. So you were in the right direction. We know the range, and we know if you want a big gamma or small gamma, but we can't say if we want this precise gamma.
Yeah, and I want to show in this graph, we can see that a really small change in gamma actually impacts a lot the number of clusters. So you see in this whole range, there is no change in the number of clusters, but in this range you have a lot of differences, and in this range also. So it will be really hard not running the algorithm actually to know where is it interesting. Is it 1? Is it 1.2? Is it 0.8? You don't know. It's really, really hard to know before running. Does anyone have a question about it? Maybe a thought? How can we... is it possible?
בעצם אתם עושים ניסוי וטעייה על הגמא, ואז בודקים את איכות המודולריות, כאילו? זה מה שקורה?
Kind of, yeah. Kind of, and that's a really good thing you mentioned over here, because we'll get to it in the end of our show.
This is exactly what we want to say,
Yeah.
that Louvain is actually really hard to predict which gamma you want, and this is where our technique will come and help everyone to check for their own gamma.
Yeah, that's a very good thing you asked. Thank you.
Okay.
Okay, so we finished the Louvain algorithm showcase. Now we'll introduce you the hierarchical clustering. So let's go. Hierarchical agglomerative clustering. Agglomerative, as I said before, is when you take two nodes and you merge them, and also calculate the weights of the merged node. So let's see, this is a dendrogram, which is the key point for hierarchical graph clustering.
Matan,
Yes.
maybe it's better if you could explain about the linkage methods.
The linkage methods, we got a couple of linkage methods. It's going to be explained.
Okay.
So yeah, this is the output of a
This is the output
cluster.
of our hierarchical graph clustering. Let's explain what we can see over here. This axis is the number of initial nodes. Like this is n, and this is the distance between the clusters. Okay, so as we can see over here, 17 and 20 were.
I think we'll explain it in the. It will be easier to understand.
It will be easier to understand with an example, but the key point is those under the bridge are the same cluster, and the distance over here is the sum of the distances inside the cluster. Okay, so we explain what is a dendrogram, which is our main goal. Our main goal of the hierarchical clustering is to create a dendrogram. And we will see here step by step how given a database
here in 2D because it's so we can visualize it easier, but you can do it in any dimension you want. We'll explain how, given a database, you can actually create your own dendrogram. So here I have a dummy database. So I have Ellen, Lisa, Joe, Max, and Cora. And we have the number of social media they have and the number of time they are going to a gym per week. Okay. Then we are plotting it here. And this is our data visualized in 2D. So this is the number of time they are going per week to the gym. And this is the number of social media they have. And we want to create a dendrogram of this data to see which cluster makes sense and actually make clusters and create the data. Okay, so let's go. So the first step of the hierarchical clustering in our case is to start with every node as its own cluster, as you can see here. Then we will try to find which are the closest pair of nodes. So to compute which are the closest pair of nodes, we can use a lot of techniques that we talked earlier in the seminar. You can use Euclidean distance, you can use Manhattan distance. We will see later in a website, you can use the maximum distance, which means it's a bit complicated, but for now, I will leave it for later. But you can use any metric you want to actually compute the distance between each node. Okay, so this is right now the empty dendrogram. We start empty, and at every iteration, we choose the closest and we merge them. In our case, it is Lisa and Joy. So after merging Lisa and Joy, there are now one cluster. And so we made this bridge, which means that Lisa and Joe are under the same cluster. And the height of this connection is the distance within the cluster. So as you might understand by yourself, every time we will merge a node to a new cluster, the height will rise, right? You cannot merge two nodes into the same cluster and lower the distance. So every time you will add a node, you will heighten the tree. Okay, now rise the questions. How would you evaluate the distances between two clusters, right? Because right now, I have Joe and Lisa in the same cluster. What is the distance between these two nodes to Carol? What do you guys think? How can we measure this distance?
The middle between both of the points of Joe and Lisa, like the average, like a centroid.
Yeah, so you chose a median, the average.
Yeah, this is complete link. No, this is a median link, I think.
Yes.
So you actually, this is one of the ideas. You're right. You can do an average of those 2 points. You're right. So over here, let's say, and you can compute the distance between the middle of the point to Caro, the middle of the point and Ellen, and the middle of the point and Max. Someone have another idea how we can maybe compute the distances between?
אולי לפי מרחקים, כאילו לפי הנקודה הכי קרובה, לפי הקלאסטרים האחרים.
יפה, this is the single linkage. This is the name of this techniques. And as you said, is to take the closest. So in this case, between Caro and Joe, I will choose the distance between only Joe and Caro. And in our other cases, Joe also and Alan, Joe and Max. And this is my way to know the distance between a whole cluster and another node. Actually, there is another last method, which is called a complete linkage, which is, it's a bit not intuitive to do that, but actually it gives us sometimes a really nice results, is to choose the farthest point from the cluster, which means if I want to compute between Caro and Joe and Lisa clusters, I will actually take Lisa and compute it to Caro. We will see in the website later how does this affect the dendrogram and the overall output, but so you know, there is 3 ways to compute the distance between a cluster and another point. You can come with your own way, right? But this is the way we are using. In our presentation, we will use the average of those 2 points to compute the to compute the distance.
I have a question?
Maximum. Yes.
About the second option, you say that you will take a single one, like Joe to Caro, Joe to Ellen, but you always take Joe, or you take Joe and
you are right.
if I have another point cluster called Johan near to Lisa, okay?
Okay, here.
So a little bit between Ellen and Lisa.
Okay, like this.
Over there.
Yeah. So
Not in
if
the
I had
cluster, another cluster.
in another cluster
So
here.
yes, here.
Okay.
So the red point is Johan. It's close to Lisa, but you choose to take from Joe or you take from Joe and Lisa.
Okay, nice question. You're right. In this example, it was a bit mistaken because Joe was closest to everyone, so I took Joe every time. But in the case, let's say I have a point over here, I will take the distance between this new point Johan and Lisa. You're right.
So you take the הכי קרוב
Yeah, the close.
to one of them, Joe or Lisa.
Yeah,
Yes.
it can be any node in the cluster. You take the closest one. You can take the middle point, like an average of those, and you can take the farthest apart. It gives interesting results. Okay, if someone have a question, this is the time. Okay, I keep going.
Yeah, I wanted to ask before you explained about comparing the clustering you do, the quality of it to a random merge. Can you?
You want to go back to the previous subject? Right now, we are explaining hierarchical clustering in global.
I just wanted to ask if you do this average linkage after you do it, you compare it to a random merge and see if it's better than it.
No.
That's
Over
my-
here,
that's
it's a
what-
different
that was my
algorithm.
question.
Over here, it's a different algorithm. We left the Louvain algorithm. Now we're explaining hierarchical clustering. It doesn't relate it to.
We are not doing a quality metric right now.
For now, it's just the distances.
Okay, we explain how we build a dendrogram given a graph.
Okay.
Okay. Okay. So as you guys said, with dorsas the way to choose the distances. So I explained it. I will not go over it again. And as you see, we choose the next two neighbors that are the closest, which was Alan and Max. Okay. And we decided that those two will be merged again. And as you can see, the height of the merge of Alan and Max is higher than Lisa and Joe, because the distance between Alan and Max is greater than the distance between Lisa and Joe, and therefore, this is why we also choose Lisa and Joe before him. Okay. Next, we will merge two clusters. So again, we will use the medium metrics. And in this case, Joe and Lisa is closer to Carol. Okay. I do a spoil for you. And that will be merged in a higher cluster. Okay. So it will look like this. Now, Lisa, Joe, and Carol are under the same cluster. So in the dendrogram, they are all connected. As you can see, this one contains Lisa and Joe, and this one contains Carol, and they are both in the same cluster at this height, which means the overall distance within this cluster is at this point. Okay. And lastly, the last step of this algorithm, which is when every node are within the same clusters. Now we have merged everyone into the same cluster, and we have our final output dendrogram, which we can see is Lisa and Joe, Carol, and Max and Alan. Now arises the question, what to do with the dendrogram? Okay, it's nice, we have a dendrogram. Now we have one cluster. What we do with this? So what we can do is actually to cut the dendrogram, which means we can take this part off, or we can cut at some height, okay? And if, let's say, we cut at this height of the dendrogram, we will have Lisa, Joe, Carol alone, Max, and Alan. Do you understand the cutting part? If I cut all these roots, right?
It's important. That's a very important part.
Yeah. If we cut here, do you understand why I have one branch from here, one branch from here, and one branch from here? You guys understand? Okay, I
Yes.
see people say yes in there. Okay, thank you. So this is our way to visualize it, right? But we don't know either a way to do it in a smart way, that we don't need to look at the graph every time. We don't need to look at the tree every time. Do you guys have an idea where to cut? Not by looking at the dendrogram?
Oria,
We'll give you a hint. It's related to something we learned in the previous lecture.
Oria, can you take that, please?
אני מנסה שנייה להבין ולעקוב אחרי הכל. הבנתי את הראשון, אתה יכול רגע לחזור לשאלה שלך?
The question is where to cut the dendrogram, given the fact that you don't want every time to look at your dendrogram and cut with your eyes. You want to know where to cut in a more specific way. You want to have a rule that helps you decide where to cut your dendrogram.
כדי בעצם לקבל רק את היחידים, כאילו לראות את החיבורים פשוט?
Yeah, you're right. And do you have a way to do it? Do you have an algorithm to cut it every time in a nice height?
אז אולי על הגובה הממוצע?
This is an idea. You maybe can choose to always cut in the middle of the heights. This can be a...
פחות או יותר יראה לך איפה זה מתחיל ונגמר, אבל אני לא בטוחה שזה יתפוס הכל פשוט.
You're right. There is some cons and pros to this idea, but this is a nice idea. You could actually implement it.
אולי לפי הגובה המקסימלי, אבל אוקיי.
I'm sad we did not add it to the presentation. It was a nice idea. But in our case, we will choose what we learned in actually a lot of clustering algorithm. We will use the elbow method again. So this is the graph of the, this is not on the same data. This is why it has more clusters and the distances, but you can see what is the distance within one cluster. So in the case we have one cluster, we have the whole distance in one cluster, and in the opposite side, we have zero cluster. Therefore, we have, as many cluster as nodes, and the distance within each cluster is zero. So there is a, let's say, a healthy middle. And again, this is our elbow method. So in this case, I will personally, choose 4. In this data, I don't know the dendrogram. This is not the same dendrogram. I don't know the dendrogram. I don't know anything.
The website.
Yeah, I don't know anything, but you can use the elbow method to know that you should cut at the height 4 of a 4-number cluster, or in our case, at the height 12. At the height 12, you will cut your dendrogram. Everyone got the point over here? Okay.
Good. So let's move on to the website. We want to show it to you. Oh. Open it twice.
We can do a short showcase.
Yeah, we'll make it short. Okay, this is the website. It's a very nice one. I'll duplicate it so you can see the dendrogram and the data. I'll explain. This is the database. You can also export and import it from your own Excel or sheet. We'll choose hierarchical clustering because that's what we're talking about. The data points, social media, and GM, and we'll add the name label to the one in the graph. Right? Yes, we'll do the same over here. Okay. Also, we got, do you remember the distance metrics? We have single linkage, we have complete linkage. Do you see the effects on the dendrogram? It's just a different way to calculate the distances, as we said earlier. It's made a really large difference in the final output. And also, we got the distance metric, which is Euclidean, we got Manhattan and maximum. I'll explain shortly about maximum because we promised earlier, but I'll do it fast because we don't have much time. The maximum metric is we have to take the x-axis and the y-axis. We take, let's say the x, okay, let's compare those two. Let's say the x-axis is 1, as we can see over here. The distance from the x-axis, and the y-axis, this is 5, this is 2, it's 3. So we'll take the tree. We'll take the maximum distance from the x's, the y or the x. Okay, let's move on. Okay, we have this dendrogram and we have this visualization of the graph. Now I want two people to tell me where would they cut the dendrogram? Where would they put the line?
Put the Euclidean distance because maximum is a bit.
Oh yeah, sure. Okay.
Including
And
me.
yeah.
Okay. Please. Someone, I need two volunteers.
So to
What was the question?
I want to know where would you put the cut? Let's say over here, or let's say over there. It could be a lot of differences. Just tell me what do you want to put
לא,
it
maybe on 3,
on
שיש
three.
לנו כאילו לא יותר מדי קלאסטרים, אבל כאילו שהם גם לא יהיו גם גדולים מדי, כאילו משהו
Nice.
באמצע כזה.
So you chose this one, right?
Yeah.
And the one?
I want it 2.5, please.
2.5 over here.
Yes.
Okay, so let's visualize this in our data. Okay, so as you can see here, we got a very large cluster. We'll choose one. We choose the purple one. If we'll have time, we'll show the red one as well. Okay, so we got a really large cluster. A cluster over here which have two and three different clusters alone. So let's see how it goes. The name over here is Cora, Max, and Ali, which I mean those are the same. So this one will be same cluster. We got Levi and Adam over here, which is in the same cluster. As you can see, they are connected in the dendrogram. So they will be in the same cluster. And we got Kim, Chen, or Chen, depends on where you're from, and Jack. They're all alone. So that will be, a minute.
No. Double.
So that will be the clusters ranchos. It seems nice. It seems nice. Now let's see the red one. Let's see what Adar chose. Adar said, as you can see, they're still connected beneath the red line. So Kim and Chen are together. This is Chen and this is Kim. So this is the differences between the clusters. Okay? Everyone understood it? Yes, I can see nod. That's in the...
Yeah, people are nodding heads. Okay.
Okay. If we will choose to cut over here, for example, we'll have I'll just mark it and then explain. If we'll choose to cut over here, we'll have a very small clusters, which I don't think it will mean much, but we'll have a very small cluster and and a lot of lone nodes. And also we have over here the elbow method, which is which is the cut that Adar chose, as we see over here. But we can also take others. It's depends on what we want to achieve. Okay, I want to say something.
I just want to say Adar choose 4 and Ran choose the next one 5.
Yeah.
So you see that using the elbow method, you will have the 2 choices that are actually good that you choose by using your eyes.
Anyone got questions?
איך מתקשר, הסברתם כאילו לחשב מרחק לפי מקסימום? אני לא הבנתי כאילו איך זה מתבטא
Yeah,
פה.
it's just another method to calculate the
The one that I do a good drawing for to explain it.
okay. So this is the axis. Wait a minute. You want to do this? Let's say we compare the distance from this node to that node. So in the y-axis, we got in the x-axis, we got this is 10, this is 8, and this is 4. So the value over here will be 4. And for the y-axis, this is 14, and this is 10. Oh, this is also 4.
No, this is 8. 8 and 4.
8.
Okay.
No,
Let's say it's 2.
Let's say it's 2 for
the sake of comparison.
Yeah. So this will be 2. The distance overall between this node and this node will be 4. This is the maximum.
הבנתי, אוקיי, תודה.
Okay. But we use Euclidean, which is as we saw earlier, it's just a line. It's gonna be like this. The distance directly. Okay. So we'll keep going with the okay. We'll keep going with the second.
Don't forget to flip the screens.
Yes. Sure.
Yeah.
Second. We'll go to the okay.
We can still see the triangle.
Yeah, do it.
No, it's okay, right?
Yeah, you can see well.
Hadar, you see the presentation, everything fine?
Yeah.
Okay.
Okay. Any more questions? No. So we finished the introduction to hierarchical graphs. Clustering, now we will show the overall of the paper algorithm.
Okay. So do you want to present it? I present it.
Yeah. So this is the main algorithm of the paper. Everyone just pay attention. This is important. We got hierarchical graph clustering by node per sampling. Node per sampling, as we said earlier, we compare pairs. In Rashi Tevot, it's CNPS. It's a new method of clustering graphs. It's also based on modularity, but we compare modularity in a different way. And it's based on how likely it is to find pairs of nodes. How likely? We use probabilities. Don't panic. We'll explain it in an easy way. You'll all understand and you'll ask questions if you don't. And the advantages of this algorithm is it's parameter free. We remember when we talked about Louvain, we got the gamma parameter. Over here, we don't have a gamma parameter, as we saw in our clustering overall. And also it outputs a dendrogram. It's very efficient. It is the nearest neighbor chain.
Which is the way we
which is the way we calculate which node is closer to the other one. We'll explain further and the method in the next slides. But let's see how it goes with the weights, the probability.
I have a question.
Yes, sure.
You mentioned that having no parameters is an advantage or a disadvantage?
It's an advantage. It's a very good advantage because remember in the Louvain algorithm, we had to choose a gamma and then run it and then hope for the best result we wanted. Over here, we just run it, and later we'll see why it's good. Why it's way better.
Yeah, but we see the big advantage that you don't need to tune everything. You run it and then you can see. And of course, because this is a hierarchical clustering algorithm, it outputs a dendrogram, which gives us a lot of information about the graph within this dendrogram. Okay. So this is our starting point. Okay, we have an adjacency matrix. How do I choose the? Oh. Okay, we have an adjacency matrix. You remember this is the distance between each pair of nodes. So let's say the distance between V1 and V2 is 0.4, as you can see over here. Let's see this edge V2, V3, it's V2, V3. And this is why we don't care about the upper triangle of the matrix, right? We don't care about what's above the diagonal, because the distance between V1 and V2 is the same from here or for here, because this is an undirected weighted graph, okay? So what we will do, given a graph, we want all the edges to be probabilities. So we do not want 20, we do not want 30, we do not want anything. We want numbers between 0 and 1, okay?
Which means we don't use distance, we use weights. It's a weighted graph, it's not a distance graph.
So this might be the input graph. If you sum all of those, it will not be 1. So this graph actually is before the processing. You will see it in the code. We process the graph before and we change the weights. Okay, to understand the algorithm, you need to understand 4 probability parts. There will be 2 explained ones now and 2 later. Okay, so we have the Wi, which means the weight of the I nodes, okay? What is the weight of a node? Okay, so right now of a vertex, right now, let's say vertex 1, we want to know what is his weight. So his weight is actually simply the sum of all his column, right? All the column that, all the edges that going from V1. So in this case, it's this one, 0.4 plus 0.4, which is equal to 0.8. Can you guys compute with me W3, someone?
כאילו 0.3 ועוד 0.5?
Yeah, exactly. We take the weight of vertex 3, which is the sum of V2, V3, V4, V3, or you can alternatively look at V3 this, and for some reason this is blank. So, okay, this is 0.8. You're absolutely right. Okay, so now this is one things you need to know, what mean weight of I, and now you need to know what is W. W is simple, it's the weight of the whole graph, right? It is the sum of all the Wi, okay? So it's simply the sum of every node edges. So you will see that we compute actually every edge 2 times, right? Because when we add up V3 weight and V2 weights, we will count this edge twice. So this is why also in the quality formula, we divide by 2m because we add everything twice. So it will be 0.3 plus 0.5 plus 0.1 plus 0.4 plus 0.4 twice. So you can see it like this. It's W1 plus W2 plus W3 plus W4. In our case, this, which is equal to 3.4. Okay? Everyone have a question about what is W, what is Wi? No. Okay.
Okay, so let's talk about how the algorithm works. It's very similar to Louvain, but we got a couple of changes. We got the pseudocode over here, and also we got it's over here in Word if you want to look at it yourself. I'll explain over the pseudocode. First of all, we initialize the vertices to be all the nodes, and we set L, which will be the dendrogram, to be empty. And then we do the aggregation part. Aggregation, as we said earlier, it's the mergent of 2 nodes. We do it n-1 times. I remember Yarin asked earlier if we do it n1 times on Louvain. So on Louvain, we don't do it. But over here, we do it n-minus time because we want to end with just 1 node at the end, as we saw earlier. So we take I and j, which is the distance between them is the minimum. We put the merged node over inside L, and then we remove the nodes from the original graph and put the merge node inside, and we update the probabilities of the nodes over here. We'll see it over there. So we said we got a nearest neighbor chain, which help you merge the nodes and keep the matrix linear. It's very important to keep the matrix linear because, as Johan said earlier, if we'll have 3 nodes over here, and when we merge this one, it will affect the distance from the other one. It will ruin the whole point, and we'll get very weird clusters, and it will mess the whole point. So,
can I precise something?
Yes.
It's really important that since when we are doing the dendrogram, the height of the merged part is at a certain height. We need that every time we merge, we keep that the next merge will be higher.
Yes.
We cannot have a new merge that will be lower.
Yeah.
Therefore, our probability heuristic, it will be explained in the next time, but it has to be linear.
So this distance cannot be lower than the distance before the merge. That's the whole point of linearity. And because we have linearity, we can use the method of nearest neighbor. What can we do about nearest neighbor? We got A and B, okay, which are closest, the closest to each other, and we want to merge them. So then we update the matrix for such that A and B will be together. And as you can see in this example, we chose the median of the distances to be the new distance. So the distance between node AB to distance C is 5.35, which is the median between 5 and 5.7. That's how we merge it. Let's go. Was there something?
Yeah.
Okay. Got any questions about it? You don't have to. We actually don't have time, so we must rush. No effect. Okay.
Okay. Now I will explain you about the probabilistic part. Okay. We understood what is W. We understood what is Wi. Okay. Now we want to understand what is P of ij and what is P of I. Okay. Firstly, I will. Okay. We already explained it. The main point of using probabilistic distance metric is to keep a linear relation instead of a metric that will not keep a linear relationship. For us, it's a bit something that we do not, we haven't seen some metric not linear, because we use most of the time, we use Euclidean metric, Manhattan metrics, all those, which are actually linear. But because we are using a weighted graph, sometimes the weighted graph cannot be represented in a Euclidean space. And therefore, using a probabilistic distance metrics actually keep the linearity over the iterations. And so this is one of the reasons we use this metric. Okay, let's go along the definitions. It's not too complicated, actually. Pij, okay, is defined to be the edge between I and j, okay, over the weight of the whole graph. Okay, so what this means? It's a proportional part of the edge Aij over the whole weights. Okay. And Pi, the probability only of node I, actually is computed as the whole connections that going outside I, okay, all the edges of I, divided by the whole weight. So actually, those are really connected. Pij is the edge of Ij divided by the whole weights, and Wi is all the edge that going outside the I node divided by the whole weight. Can someone help me to calculate PV1, V2?
Using the formula above.
Yeah, and there is a reminder. You don't need to actually tell me the number. Just tell me what to do. And to remember, the weight W is 3.4. Someone want to Help me.
0.4 divided by 3.4.
Okay, 0.4 divided by 3.4, exactly. You took the edge between V1 and the V2, and you divided by 3.4. Exactly, it's approximately 0.11. And can someone else help me with PV3?
I'll try. V3 has 0.5 and 0.3 going outside of him. So you sum them up, it will be 0.8, and then you divide it by the whole weight, which is 3.4. If I'm guessing correctly, I don't know.
I'm not guessing, it's a really nice answer. Thank you. So actually the probabilistic part of V3 is 0.23, and the edge of V1, V2 is 0.11. Okay. Is there any question up to there? If you understood the definition, that's it. It's not something that you should understand completely. This is just our metric to compute the distances between two nodes. Okay.
So I will show you the code. We finished everything up to here. We'll show you the code. It's not the end of the show. We decided to put the code in the middle because it's more related to the algorithm than the overall conclusion of the presentation. Let's see the code. Okay.
So the people that did the algorithm, they are French people. And you know, I related to French peoples, and so they decided to call their algorithm Paris. It remembers us of Boaz Ben Moshe that decided to call his satellite Satla. So they are decided to call their algorithm Paris. Paired approximately, they find a way to call it Paris.
They found a way, which is a very.
But Paris is our algorithm.
Yeah, Paris is the name of the algorithm. We actually modified the code because the authors of the paper are probably mathematics and not programmers, so it was a bit rough to understand. So we modified it a bit for you to understand it better.
Just to know, we did not change anything in the functionality. We just refactor some name. We changed some names, so it will be easier to understand what's going on.
Yeah. Okay. So first of all, we start with initiating everything. We make the process graph and make us a graph copy. It gives us the nodes. It gives us S, which is an empty list of to store the sizes of the cluster. Because remember, when we output the dendrogram, we want to see the height of the spike. We got the weights and the weights total.
Can I add something? The weight and weight total is actually what I explained earlier, the WI and W. So in this example, W total is the sum of all the weights after computing the weight probability part. For W actually contain the whole weights of the whole graph computed 1 over the whole weights.
Okay, so we also initialize CC, which is a connected components for us, like the clusters, and we got an empty dendrogram. We'll add everything over here, and then we start the node index. Since we are aggregating nodes, we'll have to merge it, and we'll have to name them in the new name. So we use the unique ID for them. Okay, let's dive into the main loop. It loops until all the nodes are processed, which is until we have only one node. We first of all put initialize the chain and put the first cluster in the chain. The chain is the matrix, actually. It's an agency matrix, as we saw earlier, 2 slides before. And we got to process this until the chain is empty, until we got everything out of there. The chain is not sorry. The chain is not the agency matrix. It's let's say a queue that uses the agency matrix. Okay. So we are using pop to pop the last node from the chain. We find the closest neighbor with this function. We actually get the node itself, which named B, and we get the distance. We take the distance as well because we want to add it to the denogram to S. And we keep doing that until the chain is empty as well. So we get a C out of the chain, and if it is B, if it's the nearest one, we are doing we keep going. We take the denogram and we add the node and the distance, and also we update the new distance overall, like the S shall A and S shall B. Okay,
Okay, so up to this part, okay, there is nothing related exactly to our algorithm. This is just an implementation of a hierarchical clustering, okay? Up to this part, this is just a way to take the nodes, find the closest neighbors, and now this is the part where when we merge two nodes to be a new cluster, this is where our algorithm come to place. So in what we are doing, we are merging them to a new nodes. You remember the pseudocode where we took two nodes, merged them into one. So our way to compute the new weight of the new node, okay, is like so. We add every neighbors of the first. You know, we take two. I will draw something instead of using my hands. If you have two nodes that you have decided to merge together, but they have some connections to other nodes, and they also may have their own this, and maybe they have a common neighbor. So you want to merge those two points into one cluster. So in our case, one node. Then you need to take, as you see, all the neighbors. So you add the weight of all the I will change color. You add all the neighbors of A, so all these edges. Then you add all the edges of B, okay? But what you might do is add the common neighbor, right? So if you add the common neighbor, you do not actually add an edge to this new vertex. You just add the weight. So this is our way to add up two nodes together. Okay.
We have to rush a bit.
Yeah. No, we have time.
We got 10 minutes.
Oh, that's so fun. Okay, so this is how we merge everything together, and everything later on, it's only for the stack implementation of the algorithm. Let's go back to here. Okay, then we increment the index of the cluster, because next time we will add node, we want to give it a unique ID. And everything here, chain append, all those stuff is only because we implemented it as a stack and we made some pop. And if we decided that two nodes should not be merged together, we need to put them back in the chain. So this is this part. Then in the end, you might have still some nodes apart that did not connected via the chain. So you process them separately. In the end, you add them up. And in the gram, you return your final dendrogram, and that's it. So this is the part. The whole point of algorithm in the code is to use the probability in the process part, and then merge the node into one. But other than that, it's a common implementation of a hierarchical cluster.
Let's see the examples. That's the plotting of the output of the algorithm. You can see here two clusters. We got to mention, as we said earlier, the distances are non-Euclidean. They are weights. So if you see outliers like a red over here, it's perfectly fine, because it might be seen like it's a an outlier, but it's kind of it's okay because the distance in the real life and in the weights are close. So this is one example. It's the best cluster with two clusters. We got few more examples. The original code had one example with 5 nodes. So we modified the code a bit so we have more interesting things to look at. More example like over here.
Yeah.
That's perfectly fine. If we would visualize it in a weighted scale, it would be okay because they would be related to each other.
May I add some comments?
Yeah.
The name homogeneous clustering, heterogeneous clustering, best distance, best cluster, those are ways to decide where to cut the dendrogram. We haven't went deep dive in those, just to know that there is some way to decide where to cut the dendrogram, but those are some of it.
Yeah, those are larger examples with more nodes. I think that's
we
it.
can go to the...
Yes, we can move on.
Is there any question up to this part? Someone have something to clarify? We have finished our algorithm presentation. So if someone have a question or something to make clear, this is the time, because then it will be the dataset. So it's clear for everyone? Okay, perfect.
Like it's clear. Let's go for the data sets. Okay, this is exciting. I'm kind of a map geek, so looking at the data set was very interesting to me. We got 3 different data sets to show you today. We got this data set which open flights. It says, let's take an airport. For example, let's take, I'll use the laser pointer. So for example, let's take this airport in Sao Paulo or Rio. We can see we got flights from Sao Paulo to Buenos Aires and also to some places in Europe. It seems like Portugal. Or let's see this airport in New Zealand, which connects to Australia a lot and to China. And the volume of the line over here, it's the amount of flights, which will be the weighted graph, which will be presented in the weighted graph of our algorithm. This is OpenStreetMap.
Okay, so our guys are from Paris, so they are really excited about Paris, and we find the place in Paris where they run the algorithm. To us, it will not talk too much because we don't know Paris like our hand, but they are very happy to show us that our algorithm successfully separated the Seine river, which is going from here. So you will see a graph that will not talk to us too much. All you need to know is that they have used the OpenStreet database, which is a GPS and a map collaborative project, and they use the connection between all the streets, and this is the way they weighted the graph, and it got result. You will vaguely see that you can see the river going in the middle, but we are not French, so we do not care about this, but still I wanted to share that with you.
Also we got Wikipedia schools, which is the links between Wikipedia's values. Let's say I don't know, the value of Ariel in Wikipedia links to the university, links to I don't know, the person that
the rector maybe.
Yes,
yeah,
the mayor and everything. But those are the main graphs they want to present.
Yeah. So in front of us we have 2 database. Okay. One is the Paris one. So as I told you earlier, it will be less talking to us. So I will leave it aside.
This is the map we saw together on the OpenStreetMap.
Yeah, we can see vaguely that there is a river coming from here, so it's always splitting over there. I will not focus on it. I will focus mainly on the world map because this is way more talking to us. So we can see that given a different cut of the dendrogram, right, we got different results. In the upper map, we have bigger clusters, right? We have whole America as one big cluster. We have Africa, Europe, and the Middle East, and
Siberia
and Russia in the same cluster, which is a huge cluster, and we have all Asia in one cluster. So we can say that this is interesting, right? We can decide that actually having whole Asia in one cluster and whole America in one cluster is good. Some people will say it's interesting, some people will say less, and we see that Alaska is in a separated cluster. We can see this as interesting. I personally prefer the bottom, and the difference about the upper one and the lower one actually is where to cut the dendrogram, right? If we cut it very high, we will have those huge clusters. Even though we have huge clusters, as you can see, we still have Alaska cluster, we still have Iceland cluster, which is exactly what our algorithm give, is that even with very big clusters, we still have very small resolution details. Okay, I need to move on because we don't have time, and this is the punch.
Okay.
Everyone that fall asleep,
Yes.
this is the point.
Welcome to the punchline. Do you remember this graph earlier? We saw it in the Louvain algorithm, the gamma distribution over here. So we can see over here, this is the graph that related to our dendrogram, which means we have the same result as running Louvain over a large amount of gammas. We can achieve it in only one run of Louvain, of node per sampling, and we got a new technique to calculate the gamma, let's say the output gamma for our dendrogram. dt is the distance it's the largest distance we have in our current step. So let's say in our last step, dt will be the distance between over here, the top of the spike until the bottom, and for this step, for this step, it will be from here to the bottom. So we take 1 divided by the distance. That will be our gamma. And that's how we can calculate the gamma related to our algorithm by node per sampling. So we got the same result as running a lot of Louvain runs from just one run of node per sampling, which means it's faster than Louvain. We don't have to use the parameter. Remember earlier when you asked, do you have to guess the parameter? So when we're using node per sampling, we don't have to guess it. We'll just get it from just a single run. It gives us a richer hierarchical information. We also have a visualization over here, but we can use the elbow method if you don't want to use it. And we get similar or better accuracy and community detection. Let's see that's a comparison. Do you want to add something?
Yeah. No, not to this slide. I just wanted to know who presented.
Yeah, go ahead.
Okay. So as we can see in the table, okay, this is a running Louvain. Note that this is for a single gamma parameter, right? After one run of Louvain, we have the result of one gamma result. So even if the time are really close to each other, you can see that the time are a bit better for our algorithm, which is interesting. By the way, this is was run on the same computer with the same specs, right? And when they run Louvain and Paris, they get the same, approximately the same, 10% faster, but this is not significant. 10% faster running time, and with Louvain you will have to run it for every gamma step. And in our case, Paris compute all those gamma-like possibilities using the dendrogram. So even if we have a similar time, the Paris actually have a way better, as Matan showed, way better results actually. So as we can see, we have an overall better time. In bold, you can see every time we are faster. There here is a bit of an outlier, I would say. And maybe the researcher opened YouTube to watch a video. Meanwhile, the algorithm was running. I don't know what happened. There is nothing mentioned about it in the paper. But you can see 10% faster in overall, and
More expected.
that's it.
Do you have question, guys? This is also this is a go further if you want to learn more about the algorithm. There's a couple of papers you can read. And do you have questions? We got our final points. Everything understood. Do you understand the big advantage of node per sampling in comparison to Louvain? This is the most important part of our show.
So to conclude, Paris is better than Louvain. כאילו,
Yes,
זה בסוף כל העניין של הניסויים שם,
Can
זה מה שהם הבינו בסוף.
Can you explain why our algorithm is so much better? Because you can say, it's almost the same time, right? So why would I use Paris? Okay, I will use the well-known method, Louvain. Why to win 30 seconds, why would I use your algorithm? Can you explain it? Hint.
לא, זה נראה לי שלכם.
Okay, so I will say it one more time so it will be clearer to everyone. The bottom graph, every X you see is one Louvain iteration running time. This means that to get one X, you need to run Louvain once. For this X, you need to run Louvain, but you don't know what you want. So to get this graph, you will have to run Louvain 100 times. But our algorithm, in one go, you actually can see the same results via the dendrogram. So the dendrogram actually hold these whole runs of Louvain in once. So this is the point. When you run Paris, you have all the information for all those runs of Louvain.
כאילו לוביין הוא כאילו בדיד והפריז הוא רציף, ואז בגלל זה כאילו יותר יעיל.
A nice way to summarize it.
Exactly. As Shira asked earlier, when you are in Louvain, you just have to guess the right gamma and hope for the best. And when you are in node per sampling, you run it once and you can get any output you want. I think. Thank you everyone for the engagement. You were really
very nice crowd,
very nice audience. Thank you very much.
Thank you.
I think we're finished.
Yeah.
תודה רבה. אוריה, את רוצה לסכם?
אני חיכיתי לזה כבר נראה לי זה מעל חצי שעה. תקשיבו, קודם כל האנגלית פרפקט, אוקיי? תקשיבו, אתם מציגים, אתם כריזמטיים, אתם יודעים בדיוק על מה אתם מדברים, אתם לא מתבלבלים, ויש ביניכם דינמיקה מטורפת, אז שפו.
האקדמית של הכוכב הבא לאירוויזיון.
אני לא צוחקת, תקשיבו, בדרך כלל אתם יודעים בוקר וזה גם זום, אבל באמת הקשבתי נראה לי ל-99% ונהניתי, אז כל הכבוד.
תודה.
טוב, חברים, הצגה מאוד מאוד יפה. היה פה את כל הדברים שבעצם אני רוצה לראות במצגת, שזה גם מוטיבציה, גם סקר ספרות, השוואה למישהו לעבודה קודמת שכבר ביצע את האלגוריתם, תיאור השיטה, תיאור הדאטה-סט, תיאור הניסויים, קוד ברמה מאוד גבוהה, והסברים גם ברמה מתמטית מאוד גבוהה. אז מאוד אהבתי את ההצגה. אני מצפה שמכאן הרמה הזו רק תישמר. לכן יואן ומתן שמו רף מאוד גבוה. אז שבוע הבא, מי מציגים? אני חושב ש...
אני ורחלי.
מי זה אני ורחלי?